Hey, this is Mel, and in this lecture, we're going to be talking about how we generate electricity with fossil fuels. So in the previous unit, we've been talking about greenhouse gases, and one of the things that we said is that we actually burn more fossil fuels to generate electricity than we do for anything else, even transportation. So the number one source of CO2 emissions in the world is for generating electricity. We're going to explore how that's done. Okay, so to start with, we're going to talk about how electricity is generated. In general, you need three things to generate electricity. You need a conductor, which is usually a metal, you need a magnetic field, and you need motion. So let's talk about these. What is a conductor? A conductor is usually copper, but it doesn't have to be, but it's a metal. So imagine a wire, right? So I've got this copper wire here, and when we talk about electricity, what we really mean is we've got the flow of electrons going down a wire. Okay, so to get that to happen, if I take a magnet, so remember a magnet has a north side and a south side, and let's say I move this magnet back and forth. If I move this magnet back and forth, what I would notice is that the little electrons would start moving down the wire. Okay? And if I move this back and forth, the electrons will change direction back and forth as well. So the conductor is a metal that allows the electrons to flow, and the motion of the magnet is what forces the electrons to move. Both those things together will generate electricity. So if I, say, wanted to power, let's say, a light bulb, then I would hook this, say, to a light bulb, okay? And as I move this back and forth, the electrons would actually move down the wire through the light, and they would continue going on a loop, and the light would light up, right? So that's electricity. So a simple demonstration is, so you may have seen something like this, that this is a hand crank generator, and inside there's a little, you see that little metal cylinder, that's got a magnet in there, and when I spin the handle, okay, the light lights up, okay. Okay. So, you need three things to generate electricity: magnetic field, conductor, and motion. So, the wires are the conductor, a physical magnet or maybe a coil wire is the magnetic field, but you need something to move it. And the thing that moves it is usually something called a steam turbine. So a steam turbine looks like a giant fan, and these steam turbines sit inside this housing, and steam comes in these holes and pushes against the blades of this turbine, and this whole thing spins around and around and around, and on the other end it's going to connect to something that's producing a magnetic field that will then spin in the same way that I just spun that little one. So steam turbines can be gigantic, and the reason they have multiple blades is so as the steam goes through them, it's the most efficient way of trying to capture all the energy from the steam, is they have multiple fan blades. So in short, what happens is steam comes in and turns the blades of the turbine, which then turn a giant version of the thing I was just holding, and that is what generates electricity. So this is what one looks like in an actual power plant. Everything's covered, so there's not much to see. But the steam comes in here. There's the fan blades would be in here, the turbine, and it's spinning this thing, which has the magnetic field in it. It's generating the electricity. That's the generator. Here's another one. Steam comes in there. Here's the generator. And in a big power plant, they'll have several of these. So here they've got several steam turbines and then turning generators here. Okay, so everything's covered. There's not a whole lot to see if you're actually to go inside a power plant. But in order to do this, you got to make steam. In order to make steam, you got to boil water. In order to boil water, you need a source of heat. Okay, so what are some of the things that we could actually burn? Well, purpose of this lecture is to talk about fossil fuels, so that's probably where we're going to start. This is a graph that's talking about CO2 emissions from different sectors, and I just want to focus on this one right here. It says electricity generation. So by burning fossil fuels, we can boil water, and this breaks it down into which fossil fuel we burn the most. And this color right here is coal, so that's number one. Number two is natural gas, that's the red, and then just a little bit of petroleum. So we, in general, in this country, do not burn oil to make electricity. We typically burn coal, number one, and number two, we burn natural gas. Now, in New Mexico, that's kind of a crappy graphic, but it's the only one I got. About 3/4 of all the electricity in New Mexico is from burning coal, and almost all the rest is from natural gas. And we're starting to see a little bit of renewables. Since this slide was made in 2009, since then, renewables has gone up a little bit, but it's still pretty low. So let's talk about coal. So what is coal? Well, coal, if you were to look at it, kind of has a black, shiny looking rock. And it starts with a swamp. So in a swamp, if you kind of think back to our lecture on dams and how we said at the bottom of a reservoir, if you dam a river and you make an artificial lake at the bottom, you have very little oxygen, right? Well, this is happening naturally in a swamp. So this water down here is very stagnant. And near the bottom, there's very little oxygen. So as material, plant, leaves, whatever, they fall down, they land in the water, they sink to the bottom. They actually get preserved because there's no oxygen down there to promote decay. And so the organic material builds up and builds up as long as these swamps stay in existence. Eventually, the material from the swamps is buried, and we would call that peat. So you can go to, say, nursery or Home Depot, wherever, you can buy bags of peat, and it looks like kind of old crappy looking leaves, and you put it in your garden as fertilizer. But eventually, if over geologic time, that peat will become buried. As it becomes buried, it gets subjected to pressure and heat. And there's this metamorphism that happens where what looks like old dead leaves turns into this black shiny rock, and then we call it coal. And high quality coal has been buried maybe miles below the surface and subjected to really high temperatures for maybe over millions of years. So it's seen a lot of heat and pressure by the time we pull it back out of the ground. But it used to be, for the most part, dead plant matter. So this is what a coal seam looks like. So you can imagine this all used to be the bottom of a swamp, long buried, subjected to heat and pressure, transformed into this coal. And in order to get to the coal, if I just go back, you've got to dig this rock away to get to the coal down here. And sometimes that's really easy. Like these guys, it's just right below the surface. But often it's not very close to the surface, and you got to go way down to get it. And there's a couple ways we do that. One is called Mountaintop Removal, and everything you see in this picture is coal. You can see all the black out here. And this used to be a mountain, and they started at the top, and they started to remove all the stuff that was not coal to get down to the coal. And that's what they're doing here. So it's a big operation, requires big equipment, big trucks, big shovels, and they have to remove a lot of material for this to be profitable. So here's a mountaintop removal. The pictures I'm showing you here are mostly from the east half of the country. So Appalachian region, a lot of this. So this was a mountain with trees on it, and they have started at the top and worked their way down. Well, if you do this, there's a lot of environmental destruction that's going on as a result of mountaintop removal. A lot of the material ends up in the rivers. You're wiping out all of the vegetation that was on top, and just from a human perspective, I mean, it's a pretty ugly thing to look at. But you can see in this picture, the black is the coal, and the beige is not coal, but they got to take it all down anyway whether it's coal or not, because they got to remove the stuff they don't want to get down to the stuff that they do want. So again, all these pictures, mountaintop removal. Okay, so it's a pretty environmentally destructive way to remove coal. Now, the other way of doing it is underground mines. So an underground mine is the coal's underground, so you drill a hole down, get a tunnel going, and this is really difficult, dangerous work. You follow that coal seam, and so environmentally, it's actually better for the environment because you're not taking down a whole mountain to get to it. You're just making a hole going down there. From a workman's perspective, it is a very dangerous job. There's coal dust, dangerous equipment, gases coming out, and by the way, everything you're mining is flammable. So the accidents happen, and coal fires happen, and occasionally we get some disasters. So here's one from 2010 where 25 people in West Virginia died when there was an explosion. So there's a methane gas buildup and it ignited. And we don't have this, so we have decent amount of safety rules in this country. But if you look at some other countries like China, they lose, usually a couple hundred people a year mining coal. It's underground. It's a very dangerous job. And like I said, everything you're mining is flammable. So why are we burning coal in the first place? Well, we just have a lot of it. And it's an accident in geologic history that the United States has a lot of coal. The reason is for millions of years, we were actually situated in a place where swamps were very common, widespread over most of the country. So if you've ever seen pictures of the Everglades today, you can imagine that type of environment all across the United States. And so all these places that are blue are places where we see a lot of coal deposits because in geologic time there was just extensive swamps that existed for millions of years. You'll notice that one of those places happens to be in northwest New Mexico. Okay, so we have a pretty good coal deposit up in here, and consequently we have coal mines in that area and coal-fired power plants. So one of the biggest ones we have is called the San Juan Generating Station. There's actually several near the Four Corners area. You can see here a pile of coal here. We've got a conveyor belt system that takes the coal up into the power plant. So on a power plant like this, you see there's 4 chimneys, right? That means there's 4 furnaces that feed 4 turbines. Okay, so here we can see 3 of them. This white that's coming out is water vapor. And a long time ago, we talked about how when you burn hydrocarbons, water vapor is a byproduct. So back then we were talking about it in terms of what makes a cloud. So I actually used a coal-fired power plant as an example back then. So what's coming out here is water vapor that's condensing, making a cloud from burning of the coal. Now, remember, the whole reason we're talking about this is because of greenhouse gases. And as we're burning coal, we're producing a lot of carbon dioxide and a little bit of, a few other things as well. But you can't see that, right? You cannot see the mercury that, if there is any that's coming out. You can't see the NOx. All you can really see is the water vapor. But near the Four Corners area, we've got several large generating stations, coal-fired power plants, because coal is so plentiful there. So here's a coal mine near Farmington, for example. Here's another one near Page, Arizona. You can see it's got 3 chimneys. Therefore, it has 3 furnaces with 3 steam turbines. There's the coal piled up right here, ready to go. Another picture of it. Here's here's the pile of coal that's getting ready to load it up into a coal-fired power plant. So in this case, the barges are bringing it down. They dump in this pile, and it comes up the conveyor belt. And the amount of coal that is burned in each coal-fired power plant is kind of staggering. So this is a coal train, and it's just a train full of coal, and generally they can be about a mile long or so. And a really big coal-fired power plant, like the one we have in the Four Corners, can burn through 3 to 5 trains of coal per day. So that gives you some kind of amount. It's a staggering amount of coal that we're burning through every single day just to keep generating electricity. So we're going to watch a little video here that was put together by a coal-fired power plant company that explains very well how it works. And they're going to go through the steps from the coal going into the power plant until electricity is generated. And it's very well done. It's animated. One of the things I want you to pay attention to is they're going to talk about several technologies that they use to clean the exhaust. So in other words, as they burn the coal and exhaust goes up the chimney, they have to clean that before it goes into the air. And they'll talk about several things that happen to clean that. And I just want to point out that the coal-fired power plants in this country are required to do those things from our Clean Air Act. So in the past, we talked about air pollution. We talked about we have these regulations for air pollution, and other countries don't necessarily have those, right? So the technologies they're talking about in this video are not the same technologies that you may find, say, in a power plant in China, okay? Because they don't have the same stringent air laws that we do. So keep that in mind. Let's watch the video.
Our process uses Powder River Basin coal from Wyoming, a subbituminous type coal, as a fuel source. When the coal arrives at our plant by train, we use a trencher and a series of long conveyors to stack coal in our yard, move it to storage silos, or send it directly to the plant. We try to keep a 37-day supply of coal, about 1.4 million tons, on the pile in our coal yard, and up to 40,000 tons in silos. Since we burn as much as 38,000 tons of coal in a 24-hour period, we need to ensure we have a substantial amount on hand. Coal moves into the plant on a conveyor and is stored in a series of silos, each one leading to a feeder, pulverizer, and ultimately to the boiler. At Plant Miller, we have 4 generating units, and each unit has 7 silos feeding into one single boiler. The coal within each silo falls into a feeder, which measures and controls the flow of coal into a pulverizer. Inside the pulverizer, coal falls onto a large rotating bowl, where it is continuously crushed by 3 large grinding wheels until it becomes the consistency of baby powder. Once the coal is a fine powder, it falls off the grinding bowl and is carried by warm primary air, maintained at 140 degrees Fahrenheit inside the pulverizer, to the boiler through 8 burner lines. When the particles of coal reach the burners, they are mixed with secondary air that has been preheated to over 500 degrees to support complete combustion inside the boiler. The combustion of the coal converts its chemical energy into thermal energy, creating a temperature inside the boiler of over 2,200 degrees. That's enough to heat the water in the series of boiler tubes to create steam, which moves onto the turbine to power the next step in our process. Superheated steam from the boiler, which is approximately 2,400 psi and 1,000 degrees, travels to the high-pressure section of the turbine, where it creates the force that turns the turbine shaft. This process causes the steam to lose temperature and pressure, so it must be sent back to the boiler to be reheated to 1,000 degrees. After reheating, the steam returns to the intermediate turbine and continues through the crossover into the low-pressure turbines. The force of the steam turns the turbine shaft, which turns the generator rotor at 3,600 revolutions per minute. This rotation, along with the induced current on the rotor inside the generator, produces voltage, completing the process of generating electricity. The generator output is 24,000 volts, which is stepped up to as much as 500,000 volts for transmission. Plant Miller uses a closed-loop circulating water system that allows water to be reused over and over. One way we use water is in the condenser, where steam enters from the turbine and condenses back into water as it passes over tubes filled with cool circulating water, which is chlorinated river water from nearby Mulberry Fork of the Warrior River. The condensed water moves into the hot well, where it re-enters the system to be reheated, turned back into steam, and continue its use throughout the plant. Let's take a closer look at the circulating water the plant uses, starting at the cooling tower. Cool water is pumped from the cooling tower basin through large pipes to the condenser to absorb most of the heat from the turbine exhaust steam, leaving us with warmer water that must be cooled. So, the warmer water is circulated back to the cooling tower, where it enters through riser lines to the top of the cooling tower fill. As the water cascades down the cooling tower fill material, it's air-cooled, allowing the heat to escape up through the natural draft cooling tower. The cooled water is collected in the cooling tower basin to be recirculated back to the plant to condense more turbine steam exhaust. Once combustion is complete, the heavier particles of ash, called bottom ash, fall into the bottom of the boiler. There, the bottom ash is crushed using clinker grinders, mixed with water and sluiced to the hydro bins, where the water is decanted and ash collected in dump trucks and either sold or moved to on-site storage. While the heavier particles of ash fall to the bottom of the boiler, the hot flue gas containing finer particles of fly ash naturally flows up to the top of the boiler and around, down, and out through the backpass section. The last section of the boiler is the economizer. Because of the shape and the flue gas flow path, some of the fly ash falls out here into hoppers. This economizer ash is pulled by vacuum, mixed and sluiced with water to the ash booster station, where it is moved to on-site storage. Flue gas, a byproduct of combustion, exits the boiler and enters the selective catalytic reducer, or SCR. While entering the SCR, ammonia is injected into the flue gas stream, where it reacts with several catalyst layers to reduce the nitrogen oxide compounds. The flue gas then passes across the air heater, where over 400 degrees of temperature are transferred from the exiting flue gas to preheat the primary and secondary air entering the plant. Next, the flue gas passes through the precipitators, where a negative charge is induced onto the fine particles of ash contained in the flue gas. That ash is then collected with an opposing charged collecting plate. These plates are then shaken by vibrating wrappers, causing the ash to fall off into hoppers at the bottom of the precipitator. The ash is then pulled with a vacuum to a collection facility for sale or storage. The flue gas then passes through the induced draft fans and to the scrubber, where booster fans pull the flue gas from the plant and push it through the scrubber absorber. In the absorber, flue gas mixes with water and limestone. The limestone reacts with and removes about 98% of sulfur dioxide, creating the byproduct of gypsum. The wet flue gas exits out the top of the absorber through to the wet stack, and a gypsum slurry stream is pulled from the bottom of the absorber and sent through a dewatering facility. Inside the dewatering facility, most of the moisture is removed from the gypsum so it can be sold for use in wallboard. When the power leaves the plant, we increase or step up the voltage for transmission purposes to as much as 500,000 volts to help minimize losses from the transmission of power. Our transmission group is responsible for the large transmission lines, towers, and substations that handle the large voltage transfer of power over long distances. Our distribution group interacts with our customers more directly and handles delivery of the power in lower voltages stepped down in substations and delivered to industrial, commercial, and residential customers in various voltages to suit their needs. It is our responsibility to provide our customers with reliable, affordable, and clean energy for their needs, and we take that very seriously. We hope you enjoyed this virtual tour of Plant Miller.
So one problem that coal-fired power plants still have is they don't know what to do with all of the ash that's left over when they're done burning the coal. So in that video, they talked about fly ash. So ash is just, if you had a fireplace and you burned some wood, you got leftover ash in the bottom when you're done, right? And so there's technology in that coal-fired power plant to keep the ash from flying out the chimney. That's what they call fly ash. It flies out, right? But there's ash left in the bottom, and they have to do something with it. And if they're burning, multiple trains full of coal a day, they're generating a lot of ash. So in this picture here, you can see what looks like this muddy area. This is coal ash, and they have to keep it wet so it doesn't blow away. And they actually don't really know what to do with it. So this big area right out in here is a ash pond. And so they take ash out of the furnace, they dump it into this big pond where it stays wet. Eventually it settles down. And here's an example of one of these ash reservoirs. So they're dumping ash into this water. You can kind of see there's an outlet here. So some of it's going out into the river. There's regulations in this country as to how much ash can get into the river system. And our current administration has been trying to weaken those regulations so that coal power plants can add more to the rivers than they have in the past. I don't know where that'll go. And people have been trying to figure out what to do with all this ash. Can we mix it in concrete to get rid of it? Can we make something out of it? Usually it's just buried. So this whole field here is all coal ash. And there's some event where there's a big erosion here, but all this dark stuff you see is coal ash, right? They just kept dumping in this field, and they had kept it wet, and they finally got something to grow on it. Really, they just don't have a solution. They don't know what to do with all of it. There's been a couple of disasters where coal ash has leaked out from a reservoir. And there's a big disaster about 10 years ago in Tennessee where one of these coal ash reservoirs broke. And about 1 a.m, all of this wet, gooey coal ash comes out and goes through town. There's chunks of roads in here. It's kind of hard to see. But this is all muddy coal ash that went through a town, wiped out some houses, comes down, gets in the river, gets carried downstream. So there's a lot of places in the United States where coal ash is becoming a problem. This is a few years old now, but this is a map showing the yellow dots are places where there are these waste ponds, these reservoirs that have coal ash sitting in them, staying wet. Places that are orange are recognized as having a high hazard potential of having a leak or a failure. And then the red ones are places where there was some sort of failure or got into the groundwater or something like that happened. So what you see here is there's a lot of red dots out here, but of course there's just a lot more coal-fired power plants out here because there's a lot more coal out here. The eastern part of the country has the majority of the coal-fired power plants. So they have the most coal ash, and therefore they have the most coal ash-related problems. Now, we could burn natural gas instead of coal. And one advantage of doing that is natural gas is a much cleaner fuel to burn. It's cleaner in that it produces less greenhouse gases than coal does. Now, coal produces all kinds of stuff. It produces CO2, ash, etc. If I burn natural gas, I still get CO2, but I get less of it, and there's no leftover ash product. And we don't have piles of coal everywhere. So all you have to do is you have to have a pipe that takes the natural gas from wherever it came from. So if you live in Albuquerque, the natural gas probably came from somewhere around Carlsbad, and down the pipe that we talked about in the past, and it comes to a power plant. And here's, for example, you can see there's 4 chimneys here, there's 4 turbines, and so they burn it, spins a turbine just like the coal does, and generates electricity that way. Here's another one. But what you don't see here is you don't see the piles of coal and all the apparatus for that. So when we talk about electricity, there's some vocabulary and some math that we got to get into. And ultimately what we're trying to do is calculate what we call carbon footprint. So where we're headed in this class is if I do something, like I turn on an appliance for a certain amount of time, how much CO2 did I produce? That's where we're headed with all this, okay? So to get there, there's a couple things that we've got to know. One is energy and one is power. And they're related to each other, and that power is how much energy you use over the time that you use it. And you can think of this as a rate of energy consumption. Now, a physicist does not like to use the term consuming energy or using energy. We don't really talk about it that way. We convert energy from one form to another. But in everyday language, we talk about things like I'm going to use energy or waste energy, right? But just to be clear, we're just converting it from one form to another. But verbally, we say things that are different than that. And I will too, because that's how we talk. So, rate of energy consumption is power. It's how fast you're using the energy. And the unit that we use for this is called the watt. Okay, so James Watt, he's a guy that helped develop the steam engine back in the 1700s. And so his last name is used today as a unit of power. And 1 watt means you're using 1 joule of energy per second. Now, that probably has no meaning to you either, because what's a joule? And it's a unit that, if you're a physicist, that would make sense to you what a joule is, but it's not something we have in everyday use. But if you think about taking an apple and lifting it 1 meter off the ground, right? So you pick it up off the ground 1 meter, that's about a joule of energy. It took you a joule of energy to do that. So 1 watt would mean you use it 1 joule of energy for every second, right? Okay, so this is power, and you've heard of this because, for one thing, you may have heard it in terms of light bulbs, right? So you might hear something like 100 watt light bulb, right? You may have heard of it that way. Or some guys can tell you that they have a 1,000 watt stereo, right? So that is another place you may have heard about it. If you have a hairdryer, on the side it might have a number like 1300 or 1350. That's its rating in watts. So watts is something you probably have heard of before. And this is all power. It's how 100 watt light bulb means it uses 100 joules of energy, of electricity, every second. That's what it means. 1,000 watt stereo is capable of using 1,000 joules a second. All right. So energy is the converse of this, power times time. So I'm just taking this formula and rewriting it, solving it. It's the same exact formula. But here's how we would do this. Let's imagine that I've got a 60 watt light bulb and I have it on for, let's say, 4 hours. How much energy did I use? And again, we're using the word use energy, consume energy, whatever. We're converting it from one form to the other, but blah, blah, blah. We know that. Okay, so what do? Math is easy. 60 watts times 4 hours. And 60 times 4 is 240. Now, I've got a unit of watts. I got a unit of hours. And when I multiply these two together, we write it as watt times hour. So this watt hour is by itself the unit of energy. Okay, so in physics there's a bunch of different units of energy. The one we're going to use in this class, and the only one we're going to use in this class, is something called the watt hour. How many watts times how many hours? You take that watt times that hour, it becomes watt hour. It's like its own thing, the watt hour. It's not watts per hour, that would be divided by, it's watts times hour, okay? So verbally you'd say this 240 watt hours. That's how you would say it, okay? So that's what that means. Now, let's do another example. And let's say I've got a 100-watt light bulb, and let's say it's a porch light, and I turn it on, and I just leave it on. Okay, so it's on for 24 hours a day. And I'd like to know how much energy I'm using in a week. Energy used in 1 week. Okay? So, energy, the formula that we just had was power times time. Okay? So power is always in watts. Time is always in hours. And sometimes you've got to do a little math to figure out what your total hours are. So in this case, my energy is, so energy is power times time. Power is 100 watts. Okay, so what's my time going to be? Well, it's on 24 hours a day, but it's on for a week, right? So there's 7 days in a week, so I multiply that by 7. Okay, so I've got 100 watts times 24 times 7. So let me do that real quick. 100 times 24 times 7 equals 16,800. Now my units are watt hours. Okay, 16,800 watt hours. Now, if you have over 1,000 watt hours, we're gonna alter that unit a little bit. Okay, if I have over 1,000, the convention that we do is we divide by 1,000 and add a K in front of it. So if I have over 1,000 watt hours, I'm going to divide the answer by 1,000 and then add a little K to the unit. All right, so like this. So 16,800 watt hours. It's over 1,000, so I'm going to divide by 1,000, and I get 16.8, and I'm going to add K to watt hours, right? So the way that verbally reads is 16.8 kilowatt hours. But people got tired of writing all that out, so there's an abbreviation for kilowatt hours. It's called kWh. And this is called, when we talk about a kWh, we say verbally it is a kilowatt hour. That's how we say it, a kilowatt hour. And the kilowatt hour is the worldwide standard for measuring electrical energy. Okay, so outside your house, you have a kilowatt hour meter because this is how the power company charges you for the electricity that you use. So here's an old school one that's got the dials on it, right? And the guys come over, and there's this, this disc spins right here, and the more electricity you use, the faster it spins. And these dials tell somebody how many kilowatt hours you have used since the last time the meter reader person came out and took a reading. And then you're charged by your kilowatt hour. So notice that this meter actually spells out kilowatt hours, and this one just says kWh, right? So when you're charged by the electric company, so for example, around here it's usually P&M is our electric company, you will get charged per kilowatt hour, right? So a rate depends on kind of where you live, but maybe somewhere between On the low end, maybe 8 cents to, depending on where you live, maybe as high as 30 cents per kilowatt hour. So we're going to learn how to calculate a carbon footprint, which just means how much carbon are we putting into the atmosphere when we do different things. And we're focusing in this class on electricity because it's kind of the easiest one to deal with. So let's imagine that all of my electricity is being generated by coal. And so if I do an activity, let's say I leave a light on for a certain number of hours or a TV on for a certain number of hours, I want to know how much coal had to be burned to do that, and as a result, how much carbon got into the atmosphere because of that. Okay, so there are modern coal-fired power plants, there are older coal-fired power plants. They're not all the same efficiency, but when you look at all of them, roughly it comes out that to generate 1 kilowatt hour, of electricity with coal, you need to burn 1 kilogram, or about 2.2 pounds, of coal. And that's about the size of a big shoebox, right? So imagine kind of an extra large shoebox full of coal. That's about how much you need. Okay, so the problems that we're going to have are all kind of the same format, which is that we'll have a scenario. We want to know how much coal is going to be burned, and then we're going to figure out from that how much CO2 is produced. So it turns out that when you burn 1 kilogram of coal, that you will produce 2 kilograms of CO2 gas. Or, if I burn 2.2 pounds to put it in our unit system, we get 4.4 pounds of CO2. So in other words, I get more CO2 out of the chimney than the amount of coal that I put in. Why would that be? Because the coal reacts, when you burn the coal, it reacts with oxygen in the air to produce more CO2. So 1 kilogram of coal makes 2 kilograms of CO2. All right, we're talking about mass of a gas, which is abstract because we don't think about gases as having mass, but they do. So how much would that be? If I had 2 kilograms of CO2, like how much is that, right? If you could see it. And if you could see it, it could fill a cube that's about 1 meter on a side. So we call that 1 cubic meter. And 1 cubic meter is about 1,000 liters. Okay, so think for every kilowatt hour that I use in electricity, I have to burn 1 kilogram of coal, which makes 2 kilograms of CO2, which would fill up 1,000 liters of CO2 gas. Okay, so those are the numbers we're going to use in this class to do the problems, but they're all kind of similar. So here's an example. So let's say I have a TV that uses 330 watts. And I have this TV on, let's say, 6 hours a day. All right? And let's say I do this every single day for a month. So we'll say 30 days. Okay, so here's the scenario. How much, ultimately, here's what I want to know. How much CO2 did I put in the atmosphere because of this? Right? So to answer that, we've got to figure out how many kilowatt hours, how much coal, and how much CO2. But it all starts on these problems with figuring out the kilowatt hours. If you know the kilowatt hours, you can get to all the other things you need to solve for. All right, so that's what we're going to do first. We're going to figure out how much energy did this take. So Energy is power times time. What's my power? 330 watts. What's my time? Okay, so it's got to be in hours. It's 6 hours a day, but I'm doing this for 30 days. So my total hours is 6 times 30, so let's multiply all that out. So I've got 330 times 6 times 30 equals 59,400 watt hours. Okay, if it's over 1,000, divide by 1,000, turn it into kilowatt hours. So I'm going to divide by 1,000, and that gives me 59.4 kWh. All right, this is what we need to do the rest. So for every we see in the beginning, for every kilowatt hour, I need to burn 1 kilogram or 2.2 pounds of coal. So let's say I ask you pounds of coal. How many pounds of coal did I have to burn in that month, right? So I take my 59.4 kilowatt hours times 2.2 pounds, 2.2 pounds of coal for every kilowatt hour. So I just take that number, 59.4 times 2.2, and I get 130.7 pounds. So that's how many pounds of coal I had to burn that month for my TV. So how much CO2 did I make? Well, if I ask for, say, pounds of CO2, then I would go back to my 59.4 kilowatt hours times 4.4. So I get 4.4 pounds of CO2 for every kilowatt hour. And now I can just take the one I just got, and I get 261.4 pounds of CO2. So that's pounds of a gas. How many liters is that? I go back to the kilowatt hours and multiply by 1,000. So if I go back to how many liters of CO2, then I go back to my kilowatt hours, which is 59.4 times 1,000 liters per every kilowatt hour, and that's pretty easy math, 59,400 liters of CO2. So in all these problems, you go back to the kilowatt hours and multiply that by 2.2 or 1 or 1,000, depending on what you're trying to solve for. Or what if the cost, financial cost, let's say they're charging me 11 cents kilowatt hour. How much money does that cost me to run my TV per month? I take 59.4 kilowatt hours times 11 cents per kilowatt hour, and 59.4 times 0.11, and I get $6.53. So if you compare these two things, the financial cost in this country is very low. Generating 59.4 kilowatt hours, that's actually quite a bit of electricity. If you had to do that manually by cranking something, I mean, it would take you weeks of work to do this. It only costs us $6.50, and yet it produces close to 60,000 liters of CO2 into the atmosphere. So this is one of the problems that we deal with in environmental science, that there is a financial cost, which is not very big, and there's an environmental cost, which can be huge. Nobody's paying for this up front, right? We pay for this, but this is really the cost that we're worried about in this class. Okay, so let's do another example. let's say I've got a 60 watt, let's say I got 60 watt porch light in the front, and I got a 100 watt porch light in the back of my house. All right, so one in the front, one in the back, and they're on 24 hours a day. How much coal do I need to burn for just these 2 light bulbs in a year? So I got to get my kilowatt hours first. Okay. What's my power? I've got a 60 watter and 100 watter. What's my time? 24 hours all year long times 365. So that gives me 160 watts times 24 times 365 hours. So I have 160 times 24 times 365. I get 1,401,600 watt hours. Okay, I got to divide by 1,000 to turn it into kilowatt hours. So divide by 1,000, and I get 1,401.6 kilowatt hours. And this is, remember, for the whole year. How many pounds of coal? Let's say I ask that question. So what we said is, if you know your kilowatt hours, multiply that by 2.2. So I take 1,401 kilowatt hours, 2.2 pounds. So 1,401.6 times 2.2, and I get 3,083.5 pounds of coal. Oops. Pounds of coal. All right. Liters of CO2. I go back to my kilowatt hours, and it's 1,000 liters for every kilowatt hour. So that gets me 1,401,600 liters of CO2. How about cost? Let's say it costs 13 cents kilowatt hour. Then I go back to my kilowatt hours, 1,401.6 times 13 cents. 1401.6 times 0.13. I get $182.21. Okay, so that's the cost in terms of financial and the cost in terms of environmental of leaving those 2 light bulbs on 24 hours a day. So these problems can get more and more complicated, but it's the same math every time. It's power times time. So we'll do one more that's slightly more complicated so you can see how you might do something like this. So we could have a scenario such as this. I've got a 60 watt porch light, and it's on for 12 hours a day. 12 hours a day. I have a 210 watt TV. It's on for 4 hours a day. Inside, I have 2 120 watt lamps. They are on for 6 hours a day. What is my carbon footprint for the year. Okay, so we're assuming the same usage every day. So what does carbon footprint mean? How much coal did I burn? How much CO2 did I produce? All right, so same math. Energy is power times time. I got to add it all up and do all the math. So I can do it piecewise. So in other words, I can say, all right, let's do the porch lights. I've got 60 watts times 12 hours times 365 days a year. I've got the TV. The TV is 210 watts times 4 hours times 365. I got the lamps. I've got 120 watt lamps, but there's 2 of them, and they're on for 6 hours a day times 365. Okay, so I'm just dividing each one of these up each time, power times time, and I can do each one and then add them all up. So 60 times 12 times 365, I get 262,800 watt hours. For the TVs, I get 210 times 4 times 365, 306,600 watt hours. And for the lamps, I get 120 times 2 times 6 times 365, 525,600 watt hours. Now what I'm going to do is go ahead and divide each of those by 1,000 and turn them into kWh. So that gets me 262.8 kWh, 306.6 kWh, 525.6 kWh. Add them all up. Take my 262.8 plus 306.6 plus 525.6 equals 1,095 kilowatt hours per year. Okay, so now if I said, all right, how many kilograms of coal would we have to burn for this? So then we'll do a couple here. So kilograms of coal, well, I can take that many kilowatt hours, 1,095, 1 kilogram of CO2, 1 kilogram of coal for every kilowatt hour means I get 1,095 kilograms of coal, right? That's pretty easy calculation. You're just multiplying by 1, right? What if I said pounds of coal? Right? Then I got 1,095 kilowatt hours times 2.2 pounds per coal. Sorry. Pounds per kilowatt hour. So I just take that, multiply that by 2.2, and you get 2409 pounds of coal. Or what if I said, how many liters of CO2? I go back to my kilowatt hours and multiply that by 1,000 liters per kilowatt hour, and I get 1,095,000, so 1,095,000 liters of CO2. Okay, etc. right? So the problems are all of a similar nature. Get it to kilowatt hours, multiply it by one of those factors, get the answer.